Hello friends, in the previous few lectures we have been looking into the high temperature mechanical behavior of materials, and in the previous lecture particularly we saw that, or in the previous two lectures we saw that to understand the mechanical behavior or the response of a material to an imposed mechanical conditions at high temperature, understanding its creep behavior is critical, or rather the creep study definitively tells us, or it gives us an information which is relevant to the practical application on how a material would behave at high temperatures. So we saw that creep has nothing to do with temperature, or in principle the definition of creep has nothing to do with temperature. It is just the time dependent behavior of materials under a given mechanical condition, but since the role of time becomes more dominant at high temperature, we choose this creep study in order to understand the behavior of materials at high temperatures. So we have two reasons for selecting the creep study or understanding the creep behavior of materials. One is the time dependent, or the influence of time on the mechanical behavior of materials gets more pronounced at high temperature, and when you look into the practical or application aspect of things, the conditions that a material is exposed to in a given application is more relevant to the condition that we construe during a creep test. So that is the reason why we would go for creep studies in order to understand the behavior of materials at high temperature, or to put it simply, if you want to use a material at high temperature, to ensure that the material will give you a good behavior, or it will not be catastrophic at high temperature, you have to go for creep study. The preferable mode or the preferable test is the creep test. Now in the previous lecture we saw that when one wants to plot, graphically represent the results of the creep study, then you need to consider one of the two mechanical conditions. So generally when you talk about mechanical testing of a material, and if you want to represent its results graphically, then you would represent it in a stress strain curve, or a load and an elongation curve. So this is a general way you would represent a mechanical behavior of a material. But since creep adds additional degree of freedom, meaning in creep you have to consider the time as well. So in addition to your stress and your strain, you have to include time, and more specifically the very definition of creep involves time. You cannot get rid of time, and time is an indispensable one. The time is the characteristic feature that defines creep, so you have to have time in your graphical representation of creep behavior. So that leaves us with two options to select from. So you have to have time in creep, so that will assume the x-axis of your graphical representation, and we have two other parameters to select from. And in the previous lectures we saw, when you want to represent the anelastic behavior, that is time dependent creep like behavior in elastic region, we chose strain because strain is something that is visible to us, that is something that we can see. So we chose time, and it was easy for us to understand what an anelastic behavior is. Now if you take the same argument, then it is also easy for us to understand the plastic deformation, or the change in the plastic deformation as the duration of loading prolongs. So that is when you increase the loading time, how much pronounced is your plastic deformation. To understand that, again strain will be helpful to us, as strain is something what we usually see. So if you take that argument, then again your creep curve would be of this form. So you have in your y-axis the strain, and at the x-axis the time. So time you cannot get rid of, because by definition creep involves time. And at the other axis you have the choice, but given that the strain is more visible to us, or it is easy for us to understand the creep behavior in terms of strain, we have that in the y-axis. Now in case of anelastic curves, we confine this strain to elastic strain, and now since creep is not confined to elastic region alone, so this will be referred to as the creep strain here. And since in this lecture and the subsequent ones we will be focusing more on creep alone, or we will be focusing largely on creep, then whenever I use this symbol here, that is the epsilon, it means creep strain. So had we been discussing in the realm of mechanical behavior, wherein we have to consider elastic strain, plastic strain, all those things, then I need to give a specific subscript in order to refer or qualify the strain to either elastic or plastic or creep. But since our discussion is largely going to be on creep, so this as it stands, the epsilon represents creep. Now we have, of all these three parameters, these two represents the mechanical behavior, and T is the characterizes the creep. So of these three we have used 2. So what does the other one mean? So what is the role of the stress here? So the stress here is assumed to be constant when you plot something like this. When you plot a creep curve involving strain and time, so that means that the other component, that is the stress, is assumed to be constant. Now when we talk about stress, we mean the mechanical condition we impose on a material. It doesn't mean that we are calculating the stress as or we are using the actual definition of stress. When I say stress, it means the mechanical condition that we impose on a material, and that is the reason why we considered this plot here. When we talked about, or when I talked about this plot here, I meant the stress strain curve or load elongation curve. So all these different variants, it means that one is the condition that we impose, the other is the response of a material. One, that is the stress or the load, it quantifies the condition that we impose on a material, and the strain or the elongation, it quantifies the response of the material to an imposed mechanical condition. So when I talk about three components in the creep, that is stress, it also means load, and strain, it could also be elongation, and time is time. So now when I choose a strain and when I choose the time, there is a possibility for me, that is I can either fix my load or make my load constant, or I can either make my stress constant. Meaning it is possible for me to forget about the cross-sectional area and just impose a constant load, or it is possible also for me to consider the initial construction area and impose the load or present the result in such a manner. However, there is a problem. Whenever I say that I assume one of the three components to be constant. So there are three interdependent components. You have stress strain relation that is shown here. You have strain time relation that is shown here, rather in the second plot. So these three are interdependent component, and if all these three components are varying, then I would end up with a three-dimensional axis or three-dimensional framework. Let me repeat it. If I have three varying interdependent components, I have stress, I have strain, and I have time. So if all these three are varying, then I need a three-dimensional frame of reference to plot the evolution. However, since we have assumed one to be constant, this allows us to plot the creep behavior in terms of two-dimensional plot involving strain and time. Since we have assumed that the mechanical condition that we impose is constant, then it is possible for us to plot the actual three-dimensional curve into two-dimensional one involving strain and time. Now, if I assume constant load, what happens is that when your material begins to deform, so ultimately every mechanical stress or mechanical test ends up with the failure of the material. And when you consider the metals or a crystalline material, before the sample fails, before the material fails, there is a decrease in the cross section. So this is something that is conventionally observed in a crystalline material. Now when I assume that my load is constant, and I have an experimental setup wherein my load is constant and I just study strain versus time, what would happen is, as the material nears its failure, as the material or the cross section area of the material decreases, then it would mean the stress which is dependent on the cross section increases. So my initial assumption of stress being constant or the mechanical condition that we impose being constant is disturbed. So to put it generally, the constant mechanical condition that we impose, which allows for a 2D representation representation is disturbed when I assume the constant load case. When I assume that when I have an experimental setup wherein the mechanical condition I'm imposing is just entirely based on load, and when I plot the results in 2 dimension, it is rather inaccurate, because as the cross section area of the sample decreases, then it means that the load or the stress correspondingly increases. So when I talk about the stress correspondingly increasing, it means now you should understand it is not the engineering stress or the general stress that we talk about, wherein the stress is defined as the ratio of load and initial cross section, but this stress is the load, and the area that we are considering is the instantaneous area, the area at that moment. There is a definite name for it. By now you should be knowing it, or if not, it's no problem, you can look it up. At least something that you have to look it up after this lecture. This could be something that you can be involved in. So this stress that we are considering here, when I say constant load, when I have an experimental setup of constant load, and when I have such a setup, the stress is not constant, or stress even or at the end of the experiment it increases, then I am talking about stress that is not a stress wherein we consider the initial cross section area, but a stress. I will also give you an example or just a hint. So this stress is the stress at that instant of loading. So this stress increases, that means the mechanical condition that we assume to be constant then gets disturbed. So the ideal way of having a creep setup is to have constant stress. So we saw that when you want to plot the creep behavior of a material, it is possible for us to fix one of the mechanical contribution. You can first fix either stress or either strain and then have a 2-dimensional plot. Now when you assume the mechanical condition that we impose, that is load or stress, to be constant, when you assume the load to be constant, to be specific, we saw that, or it is understandable that when the material ends or nears its failure, during which the cross section area of the material decreases, then what ultimately happens is that the mechanical condition that we impose changes. So what we initially assume to be constant is disturbed. To ensure that no such change occurs, then we have to use constant stress, the stress which depends not on the original cross section area but the cross section area at a given instant. So there is a name for it. You could make some effort to find, or some of you might already know. So if you choose such a condition wherein the stress defined by or characterized by the area at a given instant is constant, then you have an ideal 2-dimensional plot involving the strain in the y-axis, again the creep strain in the y-axis, and the time in the x-axis. So in general case, when you assume the mechanical condition that we impose is constant, meaning the stress that we impose with respect to the instantaneous cross sectional area is constant, then you could easily represent the creep behavior in terms of creep strain and time. Now let me just give you rather a straightforward or a conventional way a metal or a crystalline structure would respond when you impose a constant stress for a prolonged period of time. So when you expose a material, or when you impose a crystalline material, say metal or alloy, to a definite load for a prolonged period of time, conventionally or in general sense, the curve looks something like this. You have a region something like this, other. So when you impose a crystalline material to a definite stress or a constant stress for a prolonged period of time, a curve something like this would appear, or a curve something like this it will be observed. That is, this curve involves strain and time. meaning when you observe, once you impose the mechanical condition and you start measuring the strain at different times, you would end up with a curve like this, and this is conventionally observed, or this is a representative curve for the crystalline materials. Of course, there are different factors that would govern the nature of this curve. This we will study in the subsequent lecture, but generally when you take a general trend, this is how it will look like. So as you can see, forget about the physical components, forget about the strain on the y-axis and the strain at the y-axis and the time at the x-axis, forget about the physical component. Just by looking at it, you could see that you can very well discern that there are certain definite regions in this curve. So we have a curve that represents the strain over a prolonged period of time for a given imposed or for an imposed loading condition, defined by again constant stress. When you have such a setup, you calculate strain at different time steps and you have a representative plot, and this plot looks like this. And now, without even considering the what is y-axis and what is x-axis, you could see there are definite regions in this curve. For instance, in this region, the slope of this curve is gradually decreasing and changes to rather a constant region. So in the first region, the slope of this curve is gradually decreasing. There is some sort of a constant slope, but it is gradually decreasing. So this we could demarcate as 1. So this is one of the region of the curve that we have plot. We could refer to this as creep curve, because that is what we are studying essentially. So if this creep curve, a representative creep curve, there is a first region where there is a small or eventually the slope is decreasing. So there is a slope to this curve, the first region of the curve, and that is decreasing. And there is a second region where there is a marginal change in the slope. There is not much change in the slope. This characterizes the second region. And there is a third region where there is a significant increase in the slope of the creep curve. So forget about, if you even forget about all these x references and the y references, just by looking at the curve, what we now call it as creep curve, just by looking at it, you could discern there are 3 regions. The first region, the slope of the first region is gradually decreasing. The second one, there is not much change in the slope, it's more or less constant. And the third region, there is a significant increase or substantial amount increase in the slope of the curve. And based on this, one could categorize the creep curve into 3 separate regions. Now, let's get back into the making some physical sense of this curve. Let's try to understand what physical sense will this curve gives us. So what we are doing is, when you talk about creep, in relation to that of the tensile loading or tensile test, in tensile test you will gradually increase the stress and the strain gradually increases. In contrast to that, even though we might apply a tensile loading at high temperature in creep, here the load does not gradually increase or the stress does not gradually increase. That means you are imposing a definite load immediately to the material. Let me repeat, when you compare the tensile loading to the creep test, in tensile test, the load, the rate at which you are applying the load is gradual. You will be gradually increasing the load, you will be gradually increasing the stress. But in case of creep test, what you will be doing is, you will be imposing a definite value of stress, a definite value of load immediately. So what then would happen is, there will be an immediate or instantaneous elongation of the material. So the material, once you apply the load, it instantaneously elongates. So that means there will be a sharp increase in the strain at the initial stages. So let us split this creep curve involving strain and time into different segments. So when you consider the initial stages of the creep, wherein unlike tensile testing, wherein your load will be increased gradually, in creep you will be imposing a sudden load of a definite magnitude, a stress of definite magnitude, you will be imposing it suddenly. Then in response to that sudden load, there will be an instantaneous elongation. That would mean that in this region the slope will be the slope of the stress strain curve would be exceedingly strain time curve, or the creep curve would be exceedingly high. So if you want to have a really high increase in strain for a given small duration of time. So in this small duration of time, let's just say this to be T0. So this is a small duration of time, and in this small duration of time there is a sudden increase in the dimension of the material. This is because we are suddenly imposing a definite amount of load to the material, and this characterizes the creep testing. And since we are imposing a definite amount of stress suddenly, there is a sudden elongation of the material. And when you plot the elongation with respect to time, since it is sudden, the slope will also be correspondingly higher in this creep curve. Or if you consider the small amount of time, the small let's assume this T0 is close to 0 for this, or rather let me write it something like this. The T0 is close to 0, and since we are imposing the load suddenly, there is a sudden increase. Before you could discern what time it is, there is a sudden increase, and when you plot it, when you plot strain versus time curve, you could see that this slope of this curve is very high. Now this characterizes the initial stages of the creep, and that is the reason when there are some plots wherein the creep curve begins from here. So this also is a representative creep plot. However, what is missing here is this region is missing. This region, which represents an instantaneous elongation in the material. So if you compare these two creep plots, we have creep plot 1 and we have creep plot 2. When you compare these two creep plots, in this creep plot you could see that there is we have included the instantaneous elongation of the material. However, given that the instantaneous elongation of material occurs rather suddenly when you compare it with the overall scheme of things, when you compare it with the other stages of creep, when you compare that to the instantaneous elongation, it occurs suddenly. In general sense, when you plot a practical creep curve, this region would be missing, and it will begin with something like this. A more practical will be the creep curve 2, where the instantaneous elongation of the material would be missing, and the reason for it is, unlike tensile loading, in creep loading or in the creep test, you will be imposing the load suddenly. That means there is an instantaneous elongation, and when you want to plot an instantaneous process with in a similar plot or in a similar curve along with the other process that occurs at a very low rate, then it becomes difficult, and the instantaneous region will get sidelined, and it will become more insignificant. And that is the reason, for practical purposes, this instantaneous increase or this instantaneous change in the dimension of the material at the early stages of the creep testing will not be showed. And that's the reason why, for practical application, the creep curve of the form 2 is adapted. But since it is important for us to understand the theoretical aspect of things, I have included in the first curve, this region was included in order to show how in the initial stages the deformation occurs when you study the creep behavior of the material. Now after that, after the instantaneous elongation of the material, there is a decrease in the slope. After the instantaneous elongation, there is a gradual decrease in the slope. So this is what we see here. So this region, it corresponds to the, or maybe I would use a different, so this region here, it corresponds to the instantaneous elongation of the material, and this region now, let me use green, and this region now, there is a gradual change in the slope of the curve, and this change is represented here. Now immediately following the instantaneous elongation, there is a small change, or the rate at which the material is elongating decreases, and you could see there is a visible decrease in the rate at which the material is elongating, and this would form the second phase. So you have your instantaneous elongation, and there is a gradual change in the rate of elongation, and this gradual change in the rate of elongation ultimately leads to a visible state in the creep curve. Even though this gradual change in the or gradual decrease in the slope of the strain curve, it occupies a very small area in the overall creep curve. This gradual change occupies a very small area in the overall creep curve. This is not insignificant because this leads to another rather characteristic area of or the characteristic region of the creep curve. So you have two characteristic regions in the creep curve. One, that is the instantaneous elongation of the material. The other, wherein, let me use this color, wherein the strain is almost constant. You have two characteristic regions in the creep curve, and between these two you have a small region that connects these two, during which the rate of strain, during which the slope of the creep curve is gradually decreasing. So this gradual or this transient region or this region that stands between the instantaneous elongation and constant strain region, this region is the one that connects these two separate sections of the creep curve, and in this region is characterized by a gradual or a small or an eventual decrease in the slope of strain curve or eventual decrease in the slope of the creep curve. So when you talk about a strain rate in this region, the rate at which the elongation happens in this region, when you talk about or when you focus on this region that connects the instantaneous elongation to the constant strain region, this region there is a gradual decrease in the rate of elongation. So that is what we have seen here. So let us refer to this as a transient region. So what we saw is we have an initial stage, an initial region wherein the elongation is instantaneous because you suddenly apply the load, and between and after that one region that is very much visible to us is this region that is characterized by the constant strain. So if you want to plot it, it would look like something like this. When you want to just plot the second stage, it would look something like this, where the strain is more or less constant during this period of time. So this is the second stage. So we have our first stage wherein the strain is instant and it occurs instantaneously, and we have the second stage wherein the strain is constant, and between two we have our transient stage, and ultimately we have our third stage wherein the strain of the material significantly increases and ultimately fails. So in the third stage, the strain of the material increases very rapidly. The rate of increase in the strain of the material, it is very rapid, and ultimately the material fails. So what we have seen, or what we can understand just by looking into the creep curve, is there are three definite regions in the creep curve. See, the first one is the instantaneous region. In this region, the slope is high. However, this region also includes a transient region. There is a gradual decrease in the slope. So initially high slope gradually decreases and eventually leads to the second region, and this second region is characterized by a constant strain over a period of time. And the way the second stage ends is there is a sudden increase in the rate of strain at the end, and ultimately leading to the failure of the material. So the creep you can call as three stages: primary stage, secondary stage, and the tertiary stage. In the primary stage, it comprises of two parts. One, the instantaneous elongation or instantaneous strain, coupled with a transient region where the rate of strain or the slope of this curve gradually decreases, and then it leads to the second stage of the creep curve, which is a constant strain rate curve, wherein the strain over a period of time is constant, and you ultimately end up with a third stage where the strain increases, or the rate at which the strain increases is rather rapid, and ultimately it ends up in failure of the material. Now when we talk about slope of each of these curves, so far what we have done is we have characterized or we have distinguished the different regions of the creep curve based on the strain. So so far when we talked about understanding or different sections of the creep curve, we talked on or we characterized the different regions based on the rate at which the strain changed. So we characterize the different regions of the creep curve. Let's just assume this to be one of the conventional creep curves or just a representative creep curve, and we have three regions. We defined all these based on the slope of the curve. So we have our creep strain here, and we have our time here. So we categorized the different sections of the creep curve based on the slope of the curve. And what the slope of the curve in each of the region is, this is the slope of the curve, and this is nothing but the rate of strain, rate of elongation, or generally, or just simply the strain rate. So when I say, or when we see that there is three distinct regions in the creep curve which can be distinguished exclusively based on the slope of the curve, then what we are essentially saying is the strain rate in these three different regions are different. In the initial region, the strain rate is the initial region itself comprises of two parts. The strain rate is exceedingly high because the deformation is instantaneous, and after that there is a small transient region that shifts the instantaneous elongation to that of the constant elongation or constant strain rate region, and ultimately you would end up with finally a drastic increase in the strain rate that would ultimately lead to the failure. So these are the three different stages that is conventionally observed in creep curve. You have the first stage, second stage, and the third stage. So you could even technically refer to this as, so if you have your instantaneous elongation, and you have your constant strain, and ultimately you end up with rapid strain. So these you can just categorize your three different stages of the creep curve in this manner. Between instantaneous elongation and the constant strain, there will be a region called a region wherein the slope gradually decreases. So there is a decelerating creep, and here if you call this as a decelerating creep, meaning there is a gradual decrease in the slope of the curve, then the rapid strain region wherein there is a noticeable increase or drastic increase, rapid increase in the slope of the curve, then it would be accelerating creep. So it's just accelerating creep, and here you have the creep rate is constant, therefore it is steady state creep. So you have your instantaneous elongation followed by a decelerating creep, and you have your steady state creep, and then followed by accelerating creep. So these are the three critical or three characteristic components of the creep curve. You can just call it as stage 1, stage 2, and stage 3, primary, secondary, and tertiary stage. These are the different names, but if you want to talk about specifically in terms of the strain rate, then you have an instantaneous elongation or the primary creep, wherein you have your instantaneous elongation along with a decelerating creep, a transition region. These two comprise of the stage 1. The stage 1, it comprises of two. One is the instantaneous elongation and the decelerating creep, wherein there is a small change in the slope leading to the steady state region wherein the slope is more or less constant, and finally you have your accelerating creep region wherein the slope increases exceedingly, ultimately leading to the failure of the material. So you have three stages that characterizes a creep curve. You can refer to them in several different ways. However, it is important to note that the first stage comprises of two. That is one, that is instantaneous elongation coupled with a decelerating creep. There is a gradual decrease in the slope of the curve. That both these comprise of the first stage. The second stage is the steady state creep, wherein the strain rate is constant or the slope of the curve is constant. And finally, the final section that we have in the creep curve is the accelerating creep or the tertiary creep. Here, the slope of the curve is exceedingly high, and ultimately at the end of this, the material fails. So these are the three different stages in the creep curve. Now, when we talked about the initial stages, when we talked about the initial elongation when you impose the load, so that is the first stage of the creep. So we saw that these different the creep are these. So we have, if you call so forget about this 2 here, or rather we can consider that one creep curve comprises of different components, and each of the components you can represent it separately. So you can have an entire creep curve over a prolonged period of time, or you can also separate these into separate components. The reason one would want to separate it, because now when you separate it, you can talk about a specific region of the creep study. You would focus a specific region of the creep study wherein the characteristic behavior of the material is definite to that region. When I talk about, say for instance, the steady state region, which is easy for us to see visibly. If I talk about this region here, when I talk about this region here, then whatever theory is underpinning this behavior, let me repeat, I am talking about a specific region of the overall creep curve, and when I talk about that, then I would have a definite plot for it. I will not be considering the entire creep curve. I will be considering just a section of it, the steady state creep. I will have a definite plot for it, meaning I would have to focus just on this instead of the entire creep curve. Now why I would want to do it is because now in this case it becomes easy for me to study what are the theoretical reason behind this particular section of the creep curve. Instead of talking about all the different sections together, I can separate it into different sections. Instead of talking about the overall creep curve in a combined manner, I can separate it in the different sections, and I can talk about and can discuss individual sections, because the theoretical reasons for each sections are different, and when I focus on one section, then I just have to consider the theoretical reason or why such a behavior is exhibited. Now when I section this overall creep curve into different regions and study the theoretical reason for each of this region and ultimately combine it to an overall creep curve, this approach is again referred to as the phenomenological approach. And that is the reason why the approach that we take to study creep is also is termed as phenomenological approach. In the previous lecture we saw we would do a experiment and we would give equal importance to theoretical reasoning in order to arrive at a predictive results. So that is an approach we refer to as the phenomenology, and here the same approach is taken not to end up with a theoretical prediction. We don't consider end up by by sectioning this different creep curve into different segments and studying it individually by imposing a theoretical understanding. We are not ultimately combining it to give an experimental prediction or a prediction, but we are combining it to give a holistic understanding of the creep curve, and that approach is also referred to as the phenomenological approach. So please pardon my handwriting here, but you can look it up. It's just phenomenology, and so this is the approach that we take to study creep curve, or this is one of the easiest way of studying creep curve and also theorizing, or also when you want to postulate something, it is an easy way to postulate things. So what you are essentially doing is, instead of analyzing the creep curve as a whole, instead of getting a theoretical understanding of the overall creep curve, you are sectioning it and you are considering the theoretical reason for each of the sections of this curve and then combining it, not to give a prediction, which we assumed in the previous lecture, not to give a prediction, but to get a holistic understanding of the creep behavior, and that approach is referred to as the phenomenological approach. And whenever people refer to as the phenomenology of creep, this is what they mean. They, instead of considering it as the whole creep curve, they section it. They understand the theoretical reason for each of these sections, because each section is as a characteristic property. Supposing this section, which is the steady state region wherein the slope is constant, there is a theoretical reason for this constant slope during in a creep behavior, and I can then understand what is the reason for it. And then when I study other sections, for instance, if I study the final section of the failure and the rapid increase in the creep rate, and there I postulate, I present my theoretical understanding of it, then I could relate it to the previous section and then present a continuous flow of thought on why or what is the behavior of this material during the creep test. So instead of considering as a whole, we will section it. We will also present our theory by sectioning the different segments of the creep curve, we will present our understanding, and we will derive, or we will try to understand the overall creep behavior by sectioning it in different manner, and this is referred to as the phenomenology of creep. So far what we have seen is, just to give a conclusion or the summary of this lecture, so far what we have seen is, we have seen that there is a characteristic curve that creep behavior can be represented by. So if you want to represent the behavior of the creep behavior of a crystalline material, you can represent it through a characteristic curve, and this curve, just by considering the slope of the different regions in this curve, you can section it into different stages. Particularly, since we have in the x-axis we have time, it means that these different stages happen one after the other. So we can classify them as different, even though these are the sections of the curve, we call them as stages because it happens one after the other. So these different sections, they follow a chronological order, and we call them as stages. And we saw that the slope, they vary or characteristically vary for each of these regions, and in order to study the whole of the creep curve, we section it into different stages, and we focus on each and every stage, and we talk about the theoretical reason for this particular behavior in this stage, at this stage of the material, and then for each stage we do the same, and then we combine it to understand the overall creep curve. And this is a way, or this is an approach that we take to study the creep behavior of the material, and this approach is referred to as the phenomenological approach. Now, so far our one common thread in all of the discussion was, we have assumed that the mechanical condition that we impose is constant. When I say stress, what I mean is mechanical condition that we imposed is constant. It can be load, of course that would be rather inaccurate, but the correct way of expressing it is in terms of stress, that is stress which with reference to the area at a given instance. This is what our assumption is. So we assume that the stress or the load is constant, and that gives us a two-dimensional plot of strain versus time. So I just would like to end this lecture by stating that there is also another way you can assume that the strain is constant, and you can then plot the stress versus time curve. So there is also this possibility. We will see what difficulty or what is possible when you assume the strain to be constant at the beginning of the next lecture, and try to build on it. So the basic takeaway point in this lecture is, there are different stages in the creep behavior of the material. This one can explicitly understand by just considering the when you just focus on the slope of the strain versus time curve, or the conventional creep curve. When you just focus on the slope, this one could easily understand. In order to understand the overall creep behavior, we section the creep curve based on the slope, and we study it individually, and ultimately we put all together and we discuss, and this approach is called as phenomenological approach. So let's build on this understanding in the subsequent lectures, and we will try to talk about the different way one could present the creep curve, and particularly we will begin with assuming how the creep curve would look like when you assume the strain to be constant instead of the mechanical condition to be constant. So thanks for your time. We will see ourselves in the next lecture.